Hi, I want to share with you the second part of chapter 22, which is about magnetism. Of course, you're gonna find these also lecture notes. Now, the next topic is as an application of magnetism and the magnetic force, and it is called the Hall effect. What you can see here in the picture is actually a conductor that is exposed to a magnetic field, and the magnetic field it's out of the paper. Now what we can see here that whenever we're gonna have like a magnetic field and we have electrons inside that conductor, according to the rule that is the right hand rule, we are going to find that there is a force that is going to be initiated on electrons and is going to be acting so that the electrons will move to the left in this flat conductor, and I will say if we're gonna have positive charges, then they are going to move to the, okay, what did they say? If I will have electrons, okay, let me start from the beginning. First, it is like the magnetic field is going to affect charges that they are moving in a conductor. Here the velocity, yes, I'm talking about the velocity. The electrons are moving to the left, and according to the right hand rule, they're gonna have a force downward that is shown here, and we have the current that is shown is the conventional current, which is the direction of the positive. But the electrons, the actual movement of the electrons is to the left, and the magnetic field is out of the page. And we are going to find that the positive charges move to the right, and the magnetic field exerts foreign electrons and causing a voltage E. This is called Hall EMF, and if we consider the positive charges, it will create a Hall EMF called negative E. Now, if we know now the direction of the field and the current, we can find the sign of the charge carriers, that they are really in these type of conductors. Now, applications of Hall effect is one of the most important ones is determination of blood flow rate. We can use the Hall effect to determine that. As the magnetic force here, it is F equals Q, the charge, times V, the velocity, times B. And of course, because of the motion, we're gonna create an electric field, and the force for the electric field is gonna Q times E. As the magnetic force moves negative charges to one side, they can build up, but they will not be building up without a limit. Therefore, we're gonna find that the electric field caused by this separation, it will oppose the, like you can see here, this is the electric and this is the magnetic. They're gonna cancel each other, and then E can be calculated as V times B. If the electric field is uniform, then E equals EMF divided by L, where L is the width of the conductor. We can rearrange terms here so that we will be able to calculate that EMF as B times L times V. Of course, here we're going to find that all of these vectors are really perpendicular to each other. We can use that EMF when we're measuring to measure the magnetic field strength. We call these Hall probes. I'm going to show you here an example. A Hall effect flow probe is placed on an artery, applying 0.1 Tesla magnetic field across it in a setup similar to that we were talking about. What is the Hall EMF? Given that the vessel's inside diameter is 4 millimeters and the average blood velocity is 20 centimeters per second. B is 0.1 Tesla and EMF is what we are looking for. L is 410 to minus 3 meters and V, the velocity is 20 centimeters per second. Remember here, we need to convert all the numbers into meters, get rid of centimeters and millimeters. 20, 10 to minus 2 meters per second, and then EMF equals BL times V, which is 0.1 Tesla times 4, 10 to minus 3 meters times 20, 10 to minus 2 meters per second. And this is going to result in 80 micro volts. Now, we here also can talk about the magnetic force acting on a current carrying conductor. I will say here, in conclusion, all the charges that they are going to be in a conductor, they will be affected by the magnetic field, and there is a force on it. That force is going to be equal Q, the charge, times VD, we call this the drift velocity, times B times sine theta. Now I have the N, which is the uppercase N. It is the number of charge carriers in the section of wire that has a length L, and therefore that total N is going to be equal N times the volume. Lowercase m here, it is the number of charge carriers per unit volume. And I can say that the volume also equals the cross-sectional area A times L. Therefore, when I substitute all these here, we're going to have that the force, it is Q times VD, the drift velocity times B times sine theta, and AL, I can, have these all together times LB sine theta. And if you still remember, this is the calculation of the current using the drift velocity. I equals NQVD times A. And therefore, the force is going to be I times LB sine theta. This is different from when it is a charge. When it is a charge, it's going to be QV times B sine theta. When it is a conductor, it's going to be I, the current in that conductor, L, the length of the conductor, B is the strength of the magnetic field, sine theta. Now, of course, also we can use the right-hand rule to find the direction of the force. The thumb is going to be in the direction of I. The fingers, they're going to be in the direction of B, and then F is going to be out of the, the hand upwards. Of course, the torque here, we're going to find that because there is a force, and then if we have a loop, a current loop inside a magnetic field, it will experience what is really called, the torque. Torque, it is force times the distance sine theta. And here we are going to maybe study motors that they have loops of wire in a magnetic field, and when the current is passed through the loops, the magnetic field exerts torques on the loops, which rotates a shaft. Now we can say the electrical energy is converted to mechanical work. Let me show you this type of we'll say motor or physics. This morning I have, okay, okay, you can see my screen here, and you can see that this is really the case. This is the loop here where we have a battery, a current is going through the loop, and then that it's gonna be like, okay, moving because of the force that is gonna create, like I can create a more stronger magnetic field, or like the increase in the current, all is gonna increase. Okay, can you see, like, increasing also the number of the loops, and we can make the animation go very fast or faster. Okay, then these are really the factors that they can affect. Now this is here, we're gonna find the torque, and the torque, it is RF sine theta. This is from physics 120, and then the torque is gonna be W over 2, the width of the loop, divided by 2 times F sine theta, plus W over 2 F sine theta, because it's gonna act on the two sides that they are parallel with that. Okay, and therefore we're gonna have that torque equals the width times the force sine theta. Here showing you different orientation, and when the torque is 0 and when the torque is negative, and how we derive the equation. Also, I can say that the force, I can substitute the value of the force, and then finally the torque is gonna be N, the number of loops, times I, the current, times A, which is the area of the loop, times B, times sine theta. Find the maximum torque on a 100 turn square loop of a wire of 10 centimeters on a side and carries 15 amperes of current in a 2 Tesla field. And it's a very straightforward calculation. The torque equals NIAB sine theta. Now the maximum torque is going to occur when theta equals 90, so that sine 90 is 1, and tau maximum then is going to be the maximum torque, N times I times A times B, 100 times 15, the current, times the area, times the B, and that is going to be 13 newtons times meters. This is here showing you also that this is can be about meters, and we can make that pointer move over a scale. Now also we can do something to calculate what is the magnetic field created by a long straight current carrying wire, and here we are going to introduce the right hand rule too. Now the thumb is going to be in the direction of the current, and the fingers curl in the direction of the magnetic field. The magnetic field is going to be concentric circles. Now this is, we call it like a straight line current that is gonna be a very long wire, and the magnetic field can be calculated as mu0 times I divided by 2 pi r, where mu0, we call it the permeability of free space. It's a constant that equals 4 pi times 10 to minus 7 Tesla times meters divided by ampere. This is a very important constant that has to do with speed of light. R is the distance between the wire and the point, and in meters, and I is going to be the current in the wire. Find the current in a long straight wire that would produce a magnetic field twice the strength of the Earth's magnetic field force at a distance of 5 centimeters from the wire. You should know here, like this is going to be a constant given to you, that B of the Earth, it is 5 × 10⁻⁵ Teslas. And then I will say B for that wire is going to be twice of that. Then it is 2 × 5, which is 10⁻⁵, which is 1 × 10⁻⁴. Then B, it is mu0 I divided by 2 pi r, and we can calculate I to be 25 amperes. Also, we need to know how to calculate the magnetic field produced by a current carrying circular loop like this one shown here, and only at the center, like here I will say the field is not uniform, but we can find the B at the center, mu0 times I divided by 2r. Another important device, we call it a coil or a solenoid, and this is how it is really. This is the solenoid, and the magnetic field of it is gonna be B equals mu0 times N. Here it is the number of loops per unit length. Then you're gonna divide what is the total number divided by the length of the solenoid times I. N, it is uppercase N divided by L, and this is the number of loops per unit length. Here, what is the field inside a 2-meter long solenoid that has 2000 loops and carries a 1600 ampere current? Of course, first we need to find the N, the number of loops per unit length, okay, and B can be calculated as mu0 N times I. The last thing here is about the force between two parallel conductors. If we have here two wires next to each other, then one of them is going to create a magnetic field that can be measured as a mu0 I1 divided by 2 pi r, and then is going to act on the other one by a force that can be calculated as I2 LB1. We can substitute this value B1 here. Then F, we will say, because these are very long wires, we call this is the force per unit length, mu0 I1 times I2 divided by 2 pi r. Okay, this is again one of the most important applications, mass spectroscopy, where we can use the magnetic force on a charge that is coming perpendicular to the magnetic field, and by measuring the radius we will be able to find what is really the mass. This how was the mass of the electron calculated. Okay, this is all what I want to say here. Thank you very much.